Okay. Let's share screen. Okay. All right. Yeah, I guess we can do that. Sure. Okay. And yeah, can everybody see the, yeah, I don't know who actually, I forget where that shows up. I guess it shows up here. But hopefully you can see this.
Yeah,
oh, I see. Yeah,
We can
Yeah.
see it.
you can see it. Okay, that's fine. All right, so we talked about the difference between addresses and data. So remember, an address is that for our random access memory is a 12-bit value that shows where it is in the 32 banks of memory that we have, which includes the core registers, the special function registers, and all the static random access memory. The data is the actual 8-bit values stored at those locations. And a few of them don't have all the bits implemented for the special function registers. For instance, the BSR only has 5 bits. The PC LAT latch high only has 7 bits, but most of them have 8 bits, almost all of them. And all the random access memory locations have 8 bits. A lot of the registers that control the various modules may be missing a bit here or there, but you can write an 8-bit value. The bits that aren't implemented, you just write zeros, and you typically read zeros. So you just kind of ignore those bits. Okay. So we talked about that, and now I want to continue that, and I want to cover 4 more things. So I want to talk about how to pull on, I guess it's POLL, pull on a bit. And we'll explain why we might want to do that. I'll talk about how we want to configure a register. That controls a module. So a register in a module. And you've already done that. We did this example with the oscillator control register with OSCON, where we wrote 6 alpha, 0x, 6 alpha into it to set our clock speed at 4 megahertz. And then we also configured the configuration bits to set it up for internal oscillator. Okay, so that's how we're clocking it. That's how we're providing a clock to the chip. So I want to pull on a bit, configure a register, and then I want to show you how to toggle a bit. And then I want to show you how to set up an assembly language for loop. So I'm going to go over those 4 things right now. And these along with swapping the variables are what's going to be on the programming test. I will move that. I'll slide that back a day or 2 since you haven't even gotten to go to lab yet and do anything with the chip. And for those of you that didn't pick your chips up your board up last week and your little parts, if we have class tomorrow, I'll have those available, and I'll also give everybody the CP2102 and the micro USB cable. I have all that. I was thinking we'd pass that out later, but now when we start to need it for labs, but then I realize you'd really need it to power your chip. So anyway, okay. So the first thing, pull on a bit. Okay, so why would we want to pull on a bit? And what does that even mean? So we have a bunch of GPIO ports on this chip, and it is a 20-pin chip, and 2 of the pins are power and ground. 1 pin is the master clear pin, which can be an input, but if you use it as an input, then you can't use the debug features of your integrated development environment. So we want to use it with our programmer attached, and with our programmer attached, we're gonna use the master clear pin as a master clear, so it won't be an input. And then we also steal the A0 and A1 GPIO pins to be used also with our programmer attachment, so that we can use all the debug capability. And those pins are actually the clock and data pin that the debug system uses to get data in and out of the chip. So when we flash the chip, when we actually write a program in, we use the master clear pin, and we use the GPIO port A pins 0 and 1, one for the clock and one for the data, to actually write the flash memory on the PIC. And that's how we program it. And we use the snap programmer to do that. Now, I'll give you also everybody that paid the $12, you'll also get the snap, and we'll give you a cable to work with the snap too. I think I have enough. I think I have 200 cables, but if I don't, you can. Many of you probably have micro USB cables at home, but I think I have 200 cables. So we'll hopefully give you 2 cables. We'll see. I bought a bunch of those too. So anyway, so the idea is then you'll power it with the CP2102 plugged in, which eventually we will use with the PuTTY program, and use a terminal window to talk to the chip and to see data displayed on our screen from the chip. But initially we'll just use it to power it, and then you use another micro USB cable and your snap programmer to actually write the programmer to the chip. And the snap programmer looks like this. That's one right here. And the way it works, if you take your board and there is again, the programming header is right here next to UTSA, and there's an arrow on the programming header there, and there's a little bitty arrow on the snap programmer there. You can see it on this side, and the arrows have to match up. Now you'll notice that they're more that the female header on the snap has more pins than the 6 pins in the. So that's how that looks, plugs in like that. So there are some missing holes over here because the snap has eight spots on its header, and there's only 6 pins here. But we actually only use 5 pins. So part of the snap here is for other chips and other functions. And actually, I think that the snap can actually also be used with the Arduino chip. But I haven't done that yet, and I haven't verified that. But I know that's their intent to eventually do that. And so that's the snap. So you get the snap and the cable for the snap. You get the CP2102 and the cable for that. And you'll have to hook both of those up because you're going to need this to power the board. And eventually I'll give you this, and you can solder that on. The only tricky thing with this is we sort of was a little bit of a compromise, but I'm only providing a 3-volt regulator here. So the battery can only power the board at 3 volts, which is fine for the PIC, but it might be a problem for the Arduino IDE. That chip will run on that, but a lot of the devices that we might interface are going to require 5 volts. So anyway, probably that's one mod I'm going to make on the next board. I'll put on a 3 and a 5 volt regulator, which is what we used to do on the old Viva board, but we thought maybe we could get by without it. I don't know. A lot of students last year powered their boards with the CP2102 anyway and never used the battery. So I don't know. I'm still pulling my hair out about the best way to power the board. Okay, so let me put this aside again. All right, so polling on a bit. So our PIC has 20 pins. We're taking 2 of them for power and ground. We're taking 3 more away, so 5 pins total are used for powering the board and for powering the chip and for our debug and programming header. So that leaves us 15 pins. All 15, every one of those 15 pins can be a what's called GPIO, general purpose input output pin. And if that pin is set up as an input, for instance, we have a push button on the board, which you've soldered on. One's the reset and one's a push button. The reset connects to the reset pin A3. It's actually pin 3. Is that right? No, it's pin, it's 1, 2, 3, 4. Exactly. Yeah. So you have power, and then RA5, RA4, RA3 is the reset pin. So it's 4. All right. So that connects to the reset pin, but the other pin, the other button here connects to RB7. And when you punch that button, you're grounding RB7. When the button's released, RB7 is pulled up by a 100K ohm resistor. And so when the button is not pushed, if that pin is set as an input, it will read a 1. If that pin is set as an output, it's set as an, if the button is pushed, it'll read a 0. So
Sorry,
unpushed
Professor
1.
David, can you mute your mic? We're getting a lot of feedback from it.
Yeah, somebody's. Yeah, there we go. Let's see if I can see all these. Okay, so anyway, so this is the RB7 push button. It's connected to port B pin 7, and when you push it, it'll ground that pin, so it'll input a 0 if it's set up as an input. When you release it, it's pulled up to whatever the operating voltage is, so it'll read a 1. So pushed a 0, released a 1, and we're so if we wanted to condition some function on the chip, we might want to wait until might want to get to a point in our program where we would just stop and wait until that button is pushed. And so if we did that, we would call that polling on a pin. And the pin in this case would be RB7, the push button. And again, pushed, it should read 0, and unpushed, it should read a 1. So how would we wait there until it's pushed? Well, here's how we would do that. So first off, we bank cell. We bank cell port B. And then we would use our bit test F skip. So our choices are skip set or skip clear. So we'll go back and figure that out in a minute. Port B, comma 7. So it's going to test pin 7, which is RB7 in port B. And we want to skip if it's clear, which means we would go on. And if we don't skip, then we're going to execute a go to, and we're going to go to our test instruction. So we'll call this short loop A. Okay, so we'll go to short loop A. Now, so what we want to do then is we want to stay here in this loop as long as the button is not pushed, which means it should read a 1. Therefore, we want to skip when it's clear, and we want to not skip when it's set. So we're going to do bit test F skip clear, port B, comma 7. And then we'll go to loop A. So we'll stay in this tight loop until the button's pushed, and then it'll be clear. So we'll skip over that instruction, and we'll execute the next several instructions, which represent whatever the rest of our program is. All right. So that's how we poll on a pin. And in this case, we're waiting until the pin reads 0, and then we go on. So we're waiting as long as it reads a 1. All right. If on the other hand, we wanted to only stay here when the button was pushed, then we would bit test F skip set. As long as you held the button down, and you had held it down before you got here, then it would stop here and wait until you let the button go. But in this case, we want to wait here until we push the button. And so we're going to bit test F skip clear. All right. So you do have to think a little bit about which one you want to use, whether you want to use the set or the clear function, depending on what you're trying to do. All right. That's polling on a bit. Let's now go.
Professor?
Yeah, go ahead. Question?
You said push is 0 and unpush is 1?
Yeah.
Yeah, okay.
All right.
Okay, thank you. Yeah.
Yeah. Next, we're going to talk about to configure a register. Now already did that with, say, we already did that with the OSCON register. So maybe I'll just repeat that again because I want to move through this so we get all the way through. So, well, let's take a different register. Let's say we want to configure the TRIS register for port B. So let's pull up the data sheet. That's the one thing I didn't get pulled up ahead of time here. So let me do this. So should be able just to do Adobe. Okay, there's our data sheet. And then what we're going to do is, so I want to pick some register. So let me pick, well, let's pick the IO ports. So we know in our IO ports, we have to deal with some register. We always have to set up the TRIS register, which is our data direction register. And if we want to use a pin as an output, we have to set as an output. By default, they're all set as input, so we can leave it as an input. But the one thing we also have to do, if we're going to use it as an input, we have to make sure that the analog select bit is cleared for that pin. Now, there are 12 analog select channels, and there are 18 potential GPIO pins, not counting power and ground. Now, we're using the master clear pin, which is only an input pin, one of those, and we're using A0 and A1. So we're taking away those 5 pins. That leaves us 15 pins left. Of those 15 pins, a number of them have an analog function, and then some of them don't. If they don't have an analog function, then it doesn't matter because there's no ANSEL bit to mess with. But if they do have an analog function, a GPIO pin will not work as a digital input unless you clear the analog select bit. So how do you know which ones are and which ones aren't? Well, usually you should just assume they all are in case the code is ported to a different chip that has a slightly different configuration on its analog pins, so it'll still work correctly. But if you go to the if you go to these, let's see, I think it's I can't remember. Yeah, down this way. Okay, I think it's already feature with purple highlights. Table of contents goes up. Okay, so here's a page that you should be very familiar with, and I guess on the data sheet it's roughly page 10, but it could be a little before, a little after. If you hit table of contents and go up, you'll get it pretty quickly. There's a couple different packages here. This is the 20-pin PDIP, SOIC, and TSSOP, and this is the 20-pin QFN. The chip that's actually soldered on your board is an SOIC. So it's a 20-pin SOIC. So we use this column, the first column of numbers. The pins are actually labeled RA0, RA1, and so forth. RC0. Now, in the A pins, it just goes RA0 through RA6, RA5, and then it goes RB 4, 5, 6, 7. There are no RB0, 1, 2, 3s, and then RC0, 1, 2, 3, 4, 5, 6, 7, and then power and ground. So that's how those are the names for the pins, and the actual number for the pins, sorry, the actual number for the pin is here. So pin 1 is power, pin 20 is ground, pin 2 is RA5, pin 3 is RA4, pin 4, which is the master clear pin, which you see over here, is RA3. And then we're using RA0 and RA1 are the in-circuit serial programming data line and the in-circuit serial programming clock line, and the ICD date and the ICD clock. So these pins in the master clear are tied up plus power and ground. So again, 5 pins are involved in our debug header and are not available. So when you plan your projects, don't include RA0 and RA1 to be used in your project because they're tied up. You can't use them. Now, in a real application, the chip obviously in its application is not going to be connected to your programmer. So you can use these pins. What you do is you program you program your stuff in, and then you disconnect the programmer and put on jumpers or you connect them in some way to your actual application, and then you can run your application. If you need to have the debugger hooked up while you also have these pins hooked to however you're going to use them in your application, then what you have to do is buy this special header that breaks these pins out on a special die with separate actual inputs, and you have a 24-pin package instead of a 20-pin package, but it's the exact same chip. It just has these lines broken out separately for the debug purpose and for the actual GPIO purpose. And so then you can use that in your testing. You would not want to put that chip in your actual product because it's an expensive chip and it has extra pins that you wouldn't need for your project. But so that's how they kind of work around this. But in our purpose, we're not going to mess with that. We're just going to not use these 2 pins, and we're not going to use the master clear as an input. We're going to use them as their in-circuit serial programming and debug capability, and the same with the master clear. Okay, so now we're going to look at configuring. So what we want to do, I was talking about the analog features. So here are all the analog channels listed in this column right here. Okay, and you can see A to D up here. There are also analog channels for your touch sensing module. And let's see, I think that's somewhere up here. And also for the comparator. So here's your comparator port. You've got pretty much the same analog channels. And here's your capacitive touch sensing right there. So here you can see CPS 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And that's the same as the analog channels. But the comparator is a little different. It doesn't use all these, and it also uses some of the non-analog channels as outputs, but they're digital out, so that makes sense. Okay, so if there's an analog function assigned to a pin, such as RA0 and RA1, again, you're not using those anyway because they're part of your programming header. RA2 has an analog function. RA3 doesn't. That's the master clear. RA4 does. RA5 doesn't. That's connected to your green, the green light in your RGB LED. RB4 has an analog function. RB5 has an analog function, but RB6 and 7 do not. And then RC0, 1, 2, 3, and 6 and 7 have analog functions, but RC4 and 5 don't. So you have to kind of pay attention. If there is an analog function, the pin will not work as a GPIO input unless you clear the AND cell bit for that port, that pin. And if you don't clear that bit, then the analog function will still be connected. It will be the default function. And in the case of, say, this A to D, it's connected to the A to D. It's not connected to your input, and you will not be able to read the pin correctly as a digital input. Okay, so if we go back to the GPIO pins here, we see that there's several registers. There's a TRIS register, which is our data direction. That just stands for tri-state because they're tri-state buffers. So when we want to have the pin be an input, we disconnect the buffer. And all the buffer does is connect the flip-flop to the pin. Here's your tri-state buffer right there. There's your flip-flop that's associated with every pin. This is what you write when you write the latch. And when you read the latch, you read this. When you write the port, you write this flip-flop, but when you read the port, you actually read what's on the pin, assuming that your AND cell bit is set up for input and not an analog function. And here you have protection diodes on the pin. And here you have your buffer connecting the output of the flip-flop to the pin. So if this buffer is disabled, then the pin can be an input. But if this buffer is enabled, then that flip-flop is driving the pin. You're never going to, if you put a 0 in on the pin and you have a 1 in the flip-flop, you're going to read some goofy thing where you're trying to short out the output of the flip-flop. So it's going to be a problem. All right. And yeah, so, and that's also why we always write the latch, but if we have to read the pin, we have to read the port. So we don't often read the latch because you should know what you've written in the flip-flop. And we try not to write the port, although it will work. There's a small problem associated with that because of the read, modify, write functionality of all the GPIO pins on this chip, not only on this chip, but on pretty much every microprocessor. So when you read the port. When you write write the latch. Don't read the latch, don't write the port. Okay. We also have then, so you have a tris register, a port register, a latch register, and then you have the analog select register, and then you have two more registers, a weak pull-up register, which is almost useless. It is what it is useful for is if you're not using a pin and you leave it set as an input, but there's nothing attached to it, then you want to make sure that the weak pull-ups are on, and they're usually on by default, and that way you won't have noise on that pin, possibly causing interference with your chip. And then we have this input level control here, and you can switch between two different levels at which the pin will consider the input value to be a 0 or a 1. And later on in the course, we'll look at that. You actually have to calculate the values because it's a little formula, and it depends on what voltage you're running the chip at, how this is, and whether you're selecting for TTL or Schmidt trigger. And you get two different levels. And some of these are set up as Schmidt triggers by default, and some are set up as TTL by default, right? For different GPIO pins. But normally it doesn't make any difference. It only makes a difference when you're interfacing to devices that aren't clearly 0 or say 5 volts or 0 or 3.3 volts, where they may get close to the VDD value, but not quite. And then it might make a difference whether you're going to read a 1 or not. Okay, so let's set up the tris register. And this we have to do for every pin we're going to use to make sure it's configured properly for an input or an output. All right, so now back to, all right, so we're gonna configure a register. Okay, so the register we're going to configure in this case will be the tris register for port A. Now, it turns out when we're using the RA0 and RA1 as for our in circuit serial programmer, that they're sort of automatically tied to that, so they know that that's hooked up and they're committed. So it doesn't matter what you set the tris register for those values. I normally just leave them as inputs, but they're by, one of them's clearly bi-directional because it's the data line and data is coming in and out. So it doesn't really matter, that's taken over for you. And the same with the master clear based on the configuration word, the master clear, which is again RA3. So the only pins in tris A that we really have anything to do with are 5, 4, and 2. 0 and 1 and 3 are already spoken for by the in-circuit serial programmer. All right, so we'll just leave these to be zeros. So normally on 8-bit devices, I go ahead and draw out all 8 bits. I don't do it on a 32-bit device because it's too big of a pain. But on an 8-bit device, I always do this. And we'll say this is tris A. And this is bit 0, and this is bit 7. Now, again, I don't have to, 7 and 6 are not implemented on this port. So it's really only a 6-bit port. And 0, 1, and 3 are being tied up with our in-circuit serial programming. So for these, I'm just gonna assume zeros in all these places. I'm never gonna put anything else but 0 there. And I'm not gonna read anything but a 0 there either. Well, actually, I don't know. You might read a 1 here. I can't. I think there's a 1 here actually, because it can only be an input, can never be an output. In fact, you probably consider these 1s really. By default, the bits in here, we can see what those are. So the simple way to do that is to go back to our data sheet and scroll down to where we see that port. And we have 2 APF con ports, 0 and 1, and these can switch how a pin works. We'll have to deal with these as well, but we'll come back to those at a later date. So the port A registers, and then we'll have a port B register section and a port C register section. So the first registers we look at in port A, we scroll down here, we're going to see the port A data register. We're going to see the port A tris register, the port A latch register, LATA, the ANSEL A register, and the weak pull-up A register, and the input level A register. We're going to basically ignore the input level and the weak pull-ups for now. And we'll maybe touch on those later in the course, but we shouldn't ignore the ANSEL. However, in this case, the only bits we have to worry about are A2 and A4. So if we wanted to use A4 as an input, we must set this bit to a 0. And you can see by default, first off, this bit is read. You can read it and you can write it. And on power up, it's a 1. And on reset, it's a 1. So it's by default 1. And so is this one. In fact, all the ANSEL builds are all by default 1s. So in this case, we would always want to make sure if we're going to use these. But in this case, I was going to do we'll do tris A. So let's configure. It happens to be the case that we're going to use RA5 as an output for our green LED, and RA2 as an output for our red LED. So, and that's actually an orange color, it turns out. So if I were going to use it as an input, I would have to do this. But even when I use it as a digital output, you're supposed to clear this bit. So what I usually do, just to make things easy, is I would just configure this to a 0. And so let's see how we do that. So I would just write, and then we're going to come back to the tris A in a minute. But the first thing I would do is bank cell A, and then I would just CLRF all right. So that would take care of changing all the bits in the ANSEL A register that could be configured as analog inputs. It'll configure them instead to be digital inputs. So done. But now let's configure our tris register. So I'm going to bank cell that. And then what I want to do is I want to put a 0 in location 5, and I want to put a 0 in location 3. And just for grins, I'll leave location 1, RA4 as an input in case we want to use it for an input. All right, and then these aren't implemented, and these are tied up with our header. So we're just gonna write those. We'll write 1s in here. What the heck? You can write 0s if you want. It doesn't really matter. Maybe I'll just make them 0s. Okay. So that's going to be 0, 0, 0, 0, 1, 0, and then we'll put 0s up here. Again, not implemented, really doesn't matter. So now I translate this 0, 0, 0, 1, 0, 0, 0, 0 into 2 hex digits, 0x, 1, 0. And I'm going to write this in my tris A register. So what I'll do is I'll MOV literal to W 0x10. And then I will MOV W to F tris A. And now tris A will have a 1 there, 0s here. The rest of them will ignore anyway. So that's how I would configure the tris A register. For some other functional modules, for instance, if we had a functional module where we wanted to see, say like, let's look at timer 0. We're going to use that soon. So we'll go down here. Actually, I'm going to start the bottom and back into it. So here's how we set up timer 0. So we actually, timer 0 is one of these legacy things. It's a little weird. And so it has some of these things in this old legacy register called the option register, but and also there's some bits in the incon register. But most of the time, let's do timer 246 instead. Let's see, where are they? Here. Okay, so timer 246. So we'll back into it. So basically, timer 2 has a timer 2 control register here. And so let's say we just wanted to do some straightforward timing with it. Okay, so that we go to this. So timer TX con, so timer 2 con, timer 4 con, timer 6 con. The X just stands for 2, 4, or 6. So bit 7 is not implemented. Bits 6, 5, 4, and 3 are this TX outputs. Timer bit 0, 1, 2 is timer 2 on, and bits 1 and 2 are the timer 2 clock prescaler. Okay, so this is the output post scaler. This is the prescaler, and this turns on the timer. So let's say in this case, we'll do a 1-to-1 post scaler. We'll do a prescaler of 4. So we'll count 4 ticks of the system clock for every count in the timer, and then we're going to turn it on. So we would write here, we put a 0 in this unimplemented bit, 0, 0, 0, 0, 1, 0, 1. So that would actually be 0, 5 hex. And that's what we'd write in the T2 con. So you can see, depends on what you're doing. But in our case, we just implemented the tris register. And so we figured out that we had to write 0x10 in the tris register, and that would configure it the way we wanted to configure. If we were configuring the timer 2 register, then we would have had to come up with some different numbers, and we would write those in the same way. We would bank cell TMR2 CON, timer 2 con. We would move into W whatever the value we were going to use to make it work, and then we would write that out to T2 con, and that would configure T2 con. So whenever we configure a register, we basically have to do the first step is what's the value we're going to write to make it do what we want it to do, and then we have to go through this process of make cell, load up W with the correct hex value, and then we write that out into the register we're configuring. All right, so that's configuring the register. All right, now we want to do. So we'll talk about the blink thing when I actually do the blink program. So now let me do the for loop. So this is an assembly language. For loop. Now, in assembly language, we don't have a for loop. That's a C construct. So what we do instead, instead, what we're going to do is we're going to use our assembly language instructions, and we're going to make our own for loop. So the first thing we have to do, we have to create a variable, and we'll do this with the equate statement. So we'll say index EQU, and we'll put this at just for grins, we'll put this at location 0x70, which we know that 70 through 7F are our common RAM. So those are mapped to every bank. So we don't even ever have to bank cell our index. So that'll make our code a little simpler. All right. And what we first have to do is we have to preload our index with the number of times we want to do our for loop. So in C, you would do for, say, index, or INDX equals 0, index less than, say, 100, and then plus plus. And then we would have some statements in brackets here, however many statements we're going to indicate, we're going to use. Bracket the right way. All right, so that's the C construct. But in assembly, here's what we do. We first initialize our index. That's this step right here. But we can't do it on the same line. We have to write assembly language instructions to do it. So we're going to do it the way we just loaded up one of our registers we were configuring. So what we do, let's say we want to execute 100 times. So that's 100 decimal. since I don't know off the top of my head what 100 decimal is in hex, I'll just use the decimal notation. And so the first thing I'll do is bank cell. Oh, I don't have to bank cell index because it's in common RAM. So I'll just skip that. So now I'm going to move MOV L literal to W 100. I'll write it that way instead of putting in 0x. Now it's decimal. So that's base 10. So that puts 100 into W. And then I'm gonna MOV W to F and INDX. All right. So that writes out. And remember, neither of these instructions have a second operand, a destination bit. We don't have to add that. So I do this sometime before I start my loop, either right before my loop, or maybe I do it sometime before. Okay, and then now I'm going to have a label. So I start in column 0 or column 1, and I write label. So I'll call it loop B. And then my first instruction, I don't know what I'm doing in my loop. Maybe I'm gonna call a little subroutine. So I'll do call.
Can you move your paper up, please?
Sure.
Thank you.
Yeah, I'll do call my subroutine. Now I don't know what my subroutine does. I'm not worried about it, but I'm going to call it. So I'm going to do whatever the subroutine does, and then I'm going to do this. I'm going to call this subroutine 100 times because that's what I put in my index. And then what I'll do here is I'll decrement the EC, decrement F, skip on 0, and I'll use index. Now, normally I would have to bank cell this, but I don't have to because it's in common RAM. And so now I'm going to put comma F, which means I leave the result in index. I'm going to decrement index, and I'm going to leave the result there. So I'm going to start with 100, but the first time I execute this instruction, now index will be 99. Or let's say I just did it 10 times, all right? So if I did it 10 times, then the first time it's 10, and the next time it's going to be 9. So I want to leave the result though in index. So that's why I put the F there. And then I put my go-to here, which I'm going to skip when I finally zero out index. But since it's not 0, I'm going to go to loop B. And so this is going to go back to loop. It's going to call this my subroutine again. It's going to decrement the index again. So the first time through, it'll go from 10 to 9. The next time it'll go from 9 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, and 1 to 0. When it goes from 1 to 0, it's going to test it after it decrements and find that it's 0, and it's going to skip this instruction and go on to whatever code is after that. And that will be the end of the for loop. Now, how many times do I execute it? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So if I put 10 in there, I will execute it 10 times. So that makes it nice and easy. And I'm basically doing exactly a for loop that would be for, say, I equals 0, I less than 10, I plus plus. So that's exactly the assembly language for loop. Okay, so let me shift there. So now we've gone through the things I wanted to cover. Swapping X and Y, which we did on Tuesday, polling on a bit, configuring a register, and the assembly language for loop. Now I'm going to do the blink thing, but we're going to do that with the actual code. So let's see. I think I put MPLab over. Oh, it's over here. Okay. All right, let's pop it right in here, something like this. Okay, that's good. Now, so let's go through. So I showed you how to do how to configure the the two configuration words. But let's just go over that again. We go up in the window, we go down to target memory views, we go over and we go down to configuration bits. It opens up this little window, which we actually already had it open up here. And basically we want to make sure we have frequency oscillator, internal oscillator. So that's the selection. There's lots of others. External crystal high, external crystal medium, external crystal low, external RC, high speed, external clock, and then low speed, and I forget what XT. Anyway, what is XT? I don't remember. Okay, that's crystal resonator. So there are a bunch of other settings, but we're only going to use internal oscillator. And then watchdog timer off, power up timer enable off, master clear on, code protect off, code protect data off, brownout can be on or off, doesn't matter. Clock out off, internal external switchover off, failsafe clock memory off. And finally, flash memory self-write protection off. You can turn it on if you want, doesn't matter. Phase lock loop though needs to be off. Stack overflow, underflow, might as well leave that on, but we're hopefully not going to overflow our 16 level stack. Brownout will select the low level. And finally, low voltage programming on. That, make sure you always leave that on. Otherwise you'll block out your snap and we'll have to fix it for you in lab with the Picket 3 or something else. All right, then what you do is you click generate source bits. It generates them, and then you just take these and paste them in along with this one include file, which probably is already when you create your blank assembly language main module. It's usually put there as well. So you don't need to list it twice, but it does include conditional compiler assembler directives that will only include it one time. All right. Anyway, so that gives you this here. Then we're going to set up a couple of variables. I'm going to use the C block, and I'm going to start my C block at 20, variable A, variable B, and C. And then I have this, this is the reset vector. When you power up or you reset, you always start at 0. And we're going to issue a go to start command. And then if we had interrupts, we'd put those starting at location 4, and I'll show you how to do that later. We are going to use that in I think lab 3 is an I think lab 3 is an interrupt lab, but we haven't gotten there yet. No, lab 3 is the timer, lab 4 is the interrupt lab. But anyway, we're going to do that later. And then what we're going to do, we're going to write our code. Now I did go through most of this the other day. We are going to bank cell tris A. We're going to clear tris A. We're going to bank cell lat A, and we're going to set all of lat A to 1, and then we're going to move the FF to lat A. And the other thing we probably should do, put in here, just to be good, is we're going to bank BANKSEL, ANSEL A, and then clear CLRF and cell A. So that's going to take care of any of our analog bits and the ANSEL register. All right. Then in our loop, we're just going to, and again, remember, the only thing you put in column 1 are the labels. So make sure you space everything out at least one space. Bank cell lat A, we're going to clear the bit, lat A, comma 5. That's going to be our green LED. We're going to call delay. We're going to bank cell lat A when we come back from delay, because we might have changed the bank cell, the BSR in our delay routine. And then we're going to bit set F lat A5 and then call delay again, and then do it over and over and over. Okay, and here's our delay routine. Now, I'm not going to go through this. You should look at this and see if you can figure it out. Here's what the delay routine basically does. It takes 2 8-bit registers, and it does and it counts. It uses those 2 registers to count essentially 65,000 times, and so that counting routine takes about 3/4 of a second, half a second, something like that. So that gives us a little bit of delay, and that's what it does. All right. this is called a subroutine. And that's what we use in assembly language. Assembly language is not a object-oriented language like C can be. It's kind of it's a non-object oriented language. And so we do a bunch of go-tos and we do subroutines and not function calls. Okay. So, but the subroutine works similar to a function. When you call delay, it jumps down here, executes delay. When it's done with delay, it comes back and picks up on line 41 with the bank cell. All right. So now we're going to compile this. We'll test it with this little button. Compiles good. Everything's fine. No errors. And now we're going to flash it into the chip. And let's see, where's our little chip? I'm going to shrink this down. Put this down here. And we'll put our board back in here so we can see what's going on. And I'm going to connect my programmer. All right, here's my programmer. Here's my chip. Let's see. All right, and the little our RGB LED is right there. And there's our PIC chip. Okay, we're just using this to power the board. I covered this with tape because it's so bright. If I don't, it blinds everything. I need to put a bigger resistor in. All right. So now we're just gonna, I'll download it into the board, flash it into the board here, and then it should run once it downloads. And it'll say programmed and verified, hopefully. Oh, okay. So you always get this little warning. I like to keep this little warning out there. Put it in the other screen though. Okay, so now it's gonna actually flash it. And what did it do now? Oh, I see it's setting up. Okay, so it's updating firmware. So first time you use these programming tools, a lot of times it has to update the firmware for some reason. I haven't run this with it for a while. So it's going to take a minute to update the firmware. Now it's updating the FPGA in the little programmer. And okay, now it's programming verified, and now it should be working. And yep, the green LED is blinking on the board. Now it looks a little spastic because my camera is a little slow over here. It doesn't really capture it in real time, but it almost does. You can see when I move my mouse, well, it doesn't show up with the mouse so much. All right, because the mouse is not part of the camera thing. All right, but if I move my hand, you can see if I move my hand, it's kind of jerky because I don't know, it doesn't update very fast for some reason. Okay, so you can see that works. Now what I want to do, I'm gonna do this just a little bit differently. And what I want to do is I want to use the debug features and just briefly show those to you a little bit. Okay, so what I'm going to do is I'm going to click on the down arrow on either one of these, or actually I should be able to do it here. I should be able to click debug main project. So let's see what happens. So it's going to compile it again. It'll go faster this time because it doesn't have to configure the programming tool. Okay, and it looks like it's okay. It says program, and now it says running. All right, now if you see it, you can see the lights blinking. Now what I'm going to do is I'm just going to stop it with this little device there, and notice it shows me where this delay function is. And because this is counting 65,000 times, if we run it some more and stop it again, I'm sure we'll be hearing the delay function again, because this is where it spends most of its time. Now, to make this work, I'm just gonna get rid of these. I'm gonna get rid of these two delay functions, and then I'm gonna recompile the code. So I'm going to stop my debug session, and I'm going to do this again, debug main project. Okay, now that's changed. Now notice you don't see any blinking in the light. And that's because then without the delays, you won't see the blink. Even if you only put in one delay, with one delay, you'll see the light either always off or always on. And the brief moment that it's in the other state will basically, you won't see it. You might, I don't know, you might see a teeny little amount of illumination if I take out the delay, if I take out the on delay, but if I take out the off delay, then you'll just look like it's on all the time. And now with both delays gone, it's probably about half brightness all the time. Okay, well, anyway, what I want to do now though, is I'm going to stop it. Now it's not in the delay routine because I got rid of those, right? I commented them out. So now I can single step through it, and I'm going to shrink this just a little bit so you can see, so I don't have to, yeah, we'll move this over. Okay, now if I single step through, you can watch what happens. Each time I click this arrow, so the light's off, now the light's on, and now it's off. Now it's on, now it's off. Now it's on, now it's off. Now notice it actually doesn't take effect until I go to the next instruction. So I can actually use my debug tool and I can step through this program one step at a time. And as I do that, this display here in my source code actually tells me what instruction I'm executing, and then I can actually see the results. Now, the other thing that's really cool, I can open up one of my memory views, and I can go down here to target memory views, and I can look at special function registers. And I can pull up here in the special function register. So I'm interested in LAT-A, L-A-T-A. It also shows up in the port, I guess, but LAT-A. Now watch this, as I single step through, you should see, so remember 6 and 7 aren't implemented and we're changing pin 5. So right now it says pin 5 is a 0. Okay, let's see, we'll see, maybe we have to update it. Okay, the light's on. And then now we're going to bit set that pit, and that's really interesting. Well, what I expected was I would expect this bit to change, but it didn't. So what we should be seeing a change from, I don't know why that didn't work. It's really confusing me. All right, well, anyway, let me change this. So right now the light's off. And if I, it should theoretically, what I should be able to do here is, since it's bit 5, if I write 20, that should make it off. But if I go back here and I write zeros, so 0x00, that should turn it on. I didn't do it. 0x00. That should turn the light on. And it doesn't. Well, that's interesting. So yeah, it's also not showing up here. Something's screwed up. I don't know what it is. So let me get rid of this. Maybe I have. What I'll do instead, let me do, maybe I have too many. All right, I'm going to do variables, and I'm going to enter a watch window. So in my debug, I'm going to create a new watch, and I'm going to put in a special function register, and I'm going to put in latch A. All right, now it should show me what, so here's the address and here's the value. So now let's single step through. Well, I don't know. Let me reset everything. Try this again. Well, interesting. Yeah, I'm not sure why that's misbehaving.
Professor, where would you go to see the core registers being used when you're debugging?
Right here. Yeah, you go into your target memory view and special function registers. And if you there's the program counter low status, the 4 indirect registers, and then the BSR and the W register. So we should see all these changing. And we're not yeah, well, in this case, yeah, like the BSR has to be set to I think it's registered 1 or 2 for the latch, or 3 even maybe. Let's reset it and we'll see if it shows us changing even the OSCON register. It doesn't look like it's really doing anything. For some reason, it's not updating these registers. So when we do this bank cell, oh man. Okay, well, never had that happen before. I don't know why that's not working. It's quite interesting. Yeah, I don't know. Very confusing to me. Let me just, I don't know. Let's try it one more time. It should definitely show that working correctly. Yeah, I don't know. We should be able to look at the hardware stack. We should be able to look at everything. And why it doesn't do that, it's beyond me. Sometimes, I'm going to do, sometimes I always just build it one step at a time. Okay, so we're good with that. Let's program device for debugging main project. Okay, and then see if this does launch debugger main project. All right, so for some reason I'm not getting. Let's try it one more time. All right, we'll try this one more time. All right, let's see if we can see any of the special function registers. Okay, so if we stop it, so when it's running, okay, it looks like it's going to work now. Yeah, okay, so there's the BSR, it's showing 2. And now we step through it. So that means that lat A is in bank 2. And then watch as it usually shows it in red when it changes. So bank cell data, it should, and sometimes it's delayed, but so it did show, it's still showing 2 in the BSR. So it's bank selling. Yeah, so that's 2. Okay, so then let's see. We'll scroll down here to latch A. Yeah, tris. So now it is showing the tris setup correctly. It says tris A is showing everything as outputs except for the master clears a 1. So it has to be an input. It can never be an output. And then if we go down here to latch A, so it's showing right now this bit pattern in latch A. And the one we're really interested in is, so 7, 6, 5. So 5 is an output, it's a 1. All right, now, when we do this bit clearf, it should change that 1 into a 0. And then it may delay 1. Okay, now you can see that bit 5 is now a 0 and the light's on. There is like usually a one instruction delay on the updates to the registers. So now if we scroll through this, you can see it going from 1 and 0. So 1's off, 0's on. Now, so there the light. Right now, the latch A, the light is off. But if I change this from 55 to 15, well, let's see, is that right? 1, 2. Oh, that's decimal. Yeah, if I change it from 37 to 17, then it should turn the light on. So I'll do that. So 0x17. And then when I hurt that, it should turn the light on. Yeah, and it does. Okay. Now it's working correctly. I don't know why it didn't work before, but sometimes, well, that's how these integrated environments are. They're always a little squirrely. And sometimes you just have to start them again and then they behave. I don't know, don't ask me. That should have worked the first time, but it didn't. So you can see when I change this bit right here, that 0, and I might be able to click on this one right there. And if I back this up and I make this a 1, and then I hit return, it should turn the light off. Yeah, and it does. So I made this bit 5 a 1, which now makes the LED go off because again, it's a common anode LED. So my individual cathodes have to be set to 0 to turn it on and 1 to turn it off. All right, let me stop with that. What questions did you have? And we'll quit. Does anybody? Go ahead.
I have a question for the origin 4. How does that even, like, I look at the register for, or you're setting it to the 4th on origin 4 because you go to start and that's supposed to be an interrupt. How do you know that it's an interrupt?
Are you looking? Are you seeing it on my screen here?
It's after the NC block. You start, the origin start, and then you have. Oh, because in the file you have origin 4 in the lab.
Oh, yeah. So, okay. So let's look at this. I didn't actually go through the charts, but let's do this. See, I think once, yeah, here, this one. Okay, so again, so this is a compiler directive. And so there's a couple of things that in the program memory that are hardwired. The first thing is that when we reset the chip or power up the chip, it always starts at location 0. And the other thing is if we have turned on interrupts and we cause an interrupt, then it always transfers, it interrupts wherever it's executing in the program memory, and it immediately flushes the pipeline and then loads in instruction 4. And that's what it executes for the interrupt. And then when you're finished with when you finish with your interrupt, you execute the RET-FIE, return from interrupt instruction. And then it pops the address off the hardware stack that it's going to go back to, and it restores all the values in the shadow registers for the BSR, the W register, and all the indirect registers and whatnot, so that it goes back and continues where it left off without any glitch.
Okay, so that 4th register is hard coded for interrupt service.
So this isn't a register. This is a location in program memory.
Okay.
So
So
remember,
that
it's
one
a,
is, that one's always an interrupt then.
it's, yes.
Okay.
Every time you interrupt, the processor always jumps to location 4. And normally what you'll put there is either your interrupt service routine, which will save you a jump instruction, or you'll put a jump instruction to your interrupt service routine. And most of the time, it makes sense to put the interrupt service routine here and then put the actual start location after your interrupt service routine. So when you go to org, it jumps to start, but when you interrupt, it immediately starts executing your interrupt service routine, because you want interrupts to be executed as fast as possible, and you don't want to do a jump. Remember, all instructions take 2 clock cycles, with the exception of calls and jumps, and they take 2 clock cycles. So all instructions take 1 clock cycle, with the exception of calls and jumps. And and returns take 2. And when you have a 2 instruction pipeline, why do you think all the calls and jumps take 2 instructions, and all the returns? Anytime you interrupt the standard execution, not counting interrupts, even there you have to flush the thing. But I think the interrupts don't. I don't think the interrupts take 2 instructions. I think they only take 1 to start executing. But that's a little different. But when you do a go-to statement, it takes 2 instruction cycles before you execute wherever you do the go-to statement to. Why do you think that would be?
Because you got to clear the pipeline from where you were at.
That's right. Because that next instruction is already loaded in the pipeline. And so when you take the jump, you have to flush the pipeline and start the pipeline over again. And that costs you an instruction cycle. Now, why do our Intel chips and AMD chips not have that problem? Well, it's because they are conditionally executing the pipeline 10 or 12 or 15 instructions down the line. They have that many in the pipeline, and they don't want to have to flush that. So every time they hit a branch, they just conditionally execute ahead of it. And then once you finally know which branch you actually are going to take, then they dump the path that you didn't take, and they let you continue on the path that's already been pre-executed. So that's how they get around it. But in this chip, we don't do that. It's not that sophisticated. Okay, good question.
And that's because, like you were saying, it doesn't. It goes sequentially by the actual program, as opposed to like the Intel chips. It'll skip over that until it has to come back to where it's actually executed for a branch.
So what the Intel chip is actually doing, its pipeline is much bigger, and it has the ability to have parallel pipelines from every branch instruction also being calculated. And so what it does is, once it knows which path it actually would take, then it leaves that path intact and lets that be the path and gets rid of the rest of the stuff and just keeps moving along. It doesn't have to flush it and start over.
Oh, okay, that makes sense.
So when it got to that branch, it said, okay, what if I branch and what if I don't branch? And if I branch, I'm going to go to this address, so it fetches that address. And if I don't branch, I'm going to fetch this address, so it fetches that one, and it creates 2 new pipelines from that branch. And then it can predict which it doesn't know which one to use until you finally get there, but it's already moving. It's already got all that pre-calculated, so once it knows, then it discards the path it didn't take. Pretty smart, right? And then add to that mix cache predictions and cache fetches and level 1 and level 2 cache operations, and it's very complicated. And they also do branch prediction. So they know the vast majority of the time when you get to, like in a for loop, they know the vast majority of the time you get to the branch in a for loop, it's actually going to take the branch. So let's say you're doing a for loop 100 times. So 99 times it takes the branch and 1 time it doesn't. So it predicts that it's going to take the branch in that case, and it's usually right. So sometimes that's what they'll do too. They'll they'll do a branch prediction. They'll assume they're going to take the branch, and they'll just keep calculating on that assumption. And then if that assumption turns out to be wrong, and then they'll flash the queue and reload and start over. But that cost is going to be, 1% if it's 1 out of 100. So they have algorithms for doing those predictions based on what you're executing, and I don't know, they look at different things and they try and predict. So they do branch prediction, and they also are trying to predict what memory locations you're going to need in the cache, and then they're preloading the cache with that information based on their cache prediction, and trying to decrease cache hits or increase cache hits, decrease the cache misses. So yes, that's been 30 years of scholarship poured into that, and industrial secrets, and Lord knows what all. All right, what other questions? We'll quit.
For homework number 2,
Yeah,
there's, for the second question, there's a file that it says to download called assembly for VivaBoard, and we can't find that anywhere on Blackboard.
okay, let me look at that. I'm not sure about that. So let me pull that up. Let's see. Okay. So this was from 2. Yeah, download the data sheet and download from Blackboard Lab 1 files. Oh, assembly of the Viva board. Yeah, okay. So yeah, since we changed the Viva board, I guess I hid that file. Okay, so yeah. So let me see what it asked. Let me pull that back up. Let's see, where is that? Here. Oh no, that was sorry. That was here. Okay, so download from Blackboard the assembly. Turn to the schematic page and look at the schematic which has reference. Yeah, you know what? Yeah, just skip that question. I haven't uploaded a schematic for the new board, and it's actually very similar to the old one, but yeah, just delete that one. Don't do that question. I will upload a schematic though. We'll talk about that.
Okay, do you want me to just we have a class group chat that I can say that in, but I'm not sure if people will want to email from you or something, so.
Yeah, I'll send out an email. Just say ignore question 2 on the home. Yeah.
Okay, thank you.
Yeah, no problem. Yeah. The rest of it, I think, yeah, the rest of it you can do. I'm pretty sure the data sheet is on there for the linear regulator, so that'd be good. Okay. Yeah, I haven't updated that yet. Okay. Yeah, go ahead. Any other questions?
Professor, when would you poll versus interrupt?
That's a great question. So in most cases, it depends on, what other things your program is doing. If you have other things you could be doing, then you want to use interrupts. But if you have a very simple program running and you're basically dead in the water until somebody pushes a push button, well, then you can just poll on it. But if you actually could do some other things, then you should set it up as an interrupt. And sometimes people, you definitely want to use interrupts wherever you can, because they clearly are more efficient. But sometimes it doesn't really matter, because what you're doing isn't horribly efficient anyway. So yeah, so interrupts, but like on your laptop, supposing that your mouse, supposing that you polled on the mouse instead of use it as an interrupt, and so until you move your mouse, your entire desktop would be frozen, and it would only do something when you actually move the mouse. I mean, it would be stupid, because it's got all sorts of things it can be doing while you're not moving the mouse, and it could be downloading a file. It can be playing a video, and it has multiple threads running, and So it's got housekeeping stuff it's doing, checking for updates to your, to Microsoft Windows. I mean, it's doing a bunch of stuff. And so clearly there, you have to use interrupts. Otherwise it just paralyze your machine if you waited on everything. So clearly for a complicated program and a complicated set of activities, interrupts are really critical and important. For maybe a simple routine, where you're not really doing anything else, then you could pull in a bit. So does that answer your question?
Yes, sir.
All right. Okay, we'll sign off, and I'll send an email out with the don't worry about question 2 on homework 2, and I'll also when I figure out what we're doing tomorrow, I'll send out an email for that too. All right, we'll talk to you later.